Case Study C1, Part 2, Linking Factors to Symptoms. In Part 1, in the guitarist's right hand, the flexopollicis brevis was found dysfunctional, compromising the controllability of the thumb's MCP joint. Mechanically, the thumb joint chain is then under constraint, meaning that there are insufficient muscles, to fully control the joint chain. That situation is described by Scenario 5 of the peripheral factor model. Scenario 5 predicts that dysfunction may arise from conflicting compensations driven by unrelated objective functions. In this case, there are at least 3 objective functions. 1. Optimizing controllability in compensation for the defect. By hypothesis, this process is involuntary, meaning that, unaware by the musician, it is initiated and driven by the central nervous system, and it has hierarchical priority over the voluntary driven objective functions. 2. Optimizing playing motions. This objective function is driven by voluntary objectives such as quality of playing. 3. Motions resulting from the objective functions 1 and 2 must be within physiological capacities. This objective function is CNS controlled and makes use of the peripheral feedbacks. These schematics will visualize the scenario. Before the splinter trauma, the musician likely was in a very safe state. All required playing movements were feasible, even the most demanding repertoire. However, the splinter trauma moved the hand from a safe state to a state in which not all playing movements were well feasible anymore. As a result, unbeknown by the musician, his right hand entered the process of movement control changes to compensate for the defective flexopollicis brevis muscle. This schematic will visualize the model interrelationship between the 3 objective functions. Dominant is the CNS-controlled objective to increase the controllability of the thumb joint chain given the defective flexopollicis brevis. This objective drives movement compensation processes that run in the background and that feed back in the playing motions at all times. These control compensations for the defect may or may not result in a stable control state for the thumb. Movement compensations for the defect in the thumb may extend to daily life activities. In parallel, there is the effect of the defect on the execution of the existing playing motions, which after the defect likely cannot be optimally performed anymore. Therefore, the voluntary strive to maintain playing quality while compensatory control for the defect develops will require compensations in the playing technique. So the musician enters a practice loop to develop and optimize such compensations. These compensated playing motions must be within the physiological capabilities. The likelihood that these unrelated but interacting objective functions would result in a safe playing state might be small, while the possibility exists that motions develop that are dysfunctional in playing. Further practice then likely only increases dysfunctional compensations. The biomechanical diagnostics should answer the following questions. First, in slow playing, what was the link between the flexopollicis brevis deficiency and the thumb dyscontrol? Second, in slow playing, what was the link between the thumb dyscontrol and the index dyscontrol being the actual musician's complaint? Third, in fast playing, why was the thumb largely asymptomatic? And last, in fast playing, why was the index completely asymptomatic? First question. Biomechanical analysis of the link between the flexopollicis brevis deficiency and the thumb dyscontrol in slow playing. The hypothesis is that the thumb abnormal behavior results from compensation for the defect to increase thumb controllability. In schematics, the analysis considers the compensation process to increase the controllability of the thumb chain given the defective flexopollicis brevis. The analysis starts with two questions. First, what is the exact controllability problem in the thumb? Second, what are, mechanically speaking, the possible movement control compensations that can diminish or resolve the thumb controllability problem? To establish the controllability problems, thumb behavior in this video of slow playing was studied again. The video showed the following. The FPL-EPL co-contractions were most severe when the thumb was standby, i.e. when maintaining a static position in wait to strike a string. The FPL-EPL co-contractions disappeared when the thumb extended to play a string. In this brief extension phase, thumb control almost looked normal. After string strike, when the thumb returned to a standby position, the FPL-EPL co-contractions reappeared. In conclusion, there was a fundamental difference in thumb behavior between a static standby position, in which the FPL-EPL co-contractions were severe, and when in motion, during which no significant FPL-EPL co-contractions occurred. In the following sections, hypotheses are presented to explain these differences. The present section focuses on explaining why FPL-EPL co-contractions would occur in the standby position. Mechanically, what are the possible movement control compensations that can diminish or resolve the thumb controllability problem in the standby position? Distinction can be made between intrinsic and extrinsic control compensations. Intrinsic control compensations consist of enhancing thumb control by the thumb muscles themselves. Two mechanical possibilities were already analyzed in part 1 of this lecture. FPL-EPL co-contractions to produce a flexion moment at the MCP joint that is balanced by the extensor pollicis brevis, putting the IP joint in its flexion end position. With the IP joint in its end position, the MCP joint is fully controlled, with the FPL as flexor and the EPL and EPB as extensors. The biomechanical conditions for these compensations were discussed in part 1 of this lecture. Extrinsic control compensations consist of enhancing thumb control by external support. External support can be obtained from two sources. By putting the thumb tip on the strings in standby position. However, this possibility was not observed in the video. And the other possibility is that the index finger provides support to the thumb. See video at the next slide. This video shows both intrinsic and extrinsic control compensations. The beginning shows FPL-EPL co-contractions when the thumb is in standby position, and especially the tendency to flex the IP joint in its flexion end position. Near the end, the video shows the thumb tip seeking firm contact with the index up to the point at which the index plays strings while the thumb maintains contact with the index throughout the entire keystroke motion. Technical intermezzo. What are the mechanics involved in enhancing thumb controllability by external support? The answer to this question relies on the following theorem on multi-articular mechanics. To maintain static equilibrium in an unloaded massless joint chain, one more muscle is required than is needed to maintain static equilibrium in a loaded chain. The theorem can be simply demonstrated for a single joint. Consider a planar joint moving in the plane of the slide. The joint can be kept in equilibrium against an external force K by a single muscle M as shown in A. However, without external load, keeping the joint in active static equilibrium, i.e. with non-zero muscle forces, requires two muscles in an antagonistic configuration. These antagonistic muscles then work synergistically to maintain the joint in position. Mechanically, the moment of the external load K at the joint in A is equivalent to the moment of muscle M2 at the joint in B. This also holds for joint chains with multiple joints. Actively maintaining static equilibrium in an unloaded joint chain requires one more muscle than when the chain is loaded. Application of the theorem to the thumb. The flexopolis brevis defect results in a thumb with one muscle too few to fully control the degrees of freedom in the joint chain. By the theorem, a single well-directed external force K can replace the missing flexopolis brevis muscle function. With this external force, the remaining muscles can then keep the thumb joint chain in static equilibrium. The thumb's position is then fully controlled so that no compensatory FPL-EPL co-contractions would be necessary anymore. What would be a well-directed external force to keep the thumb balanced in standby position? In other words, what would be the optimal direction for an external force K at the thumb tip to achieve full static thumb equilibrium with minimal muscle forces? In the next slides, a planar thumb model is used to determine optimal external force directions. To investigate the functional directions of an external force supporting the thumb, a model of the biarticular chain of MCP and IP joints suffices. The thumb muscles that control the CMC joint are intact, meaning that the CMC joint position can be controlled irrespective of the flexopolis brevis defect. Therefore, the CMC joint does not need to be included in the model equilibrium equations to determine effective external force directions to compensate for the flexopolis brevis defect. For this specific purpose, it suffices to model the thumb's biarticular chain consisting only of the MCP and IP joints. For the biarticular chain, a method was published allowing to graphically estimate the muscle forces as a function of the direction of an external load K. This graphic method will be further used. The model consists of the thumb chain geometry and position in the P-plane, parameterized by the joint angles, the segment lengths, the moment arms of the tendons at the MCP and IP joints, and the direction of the external force K, which determines the moment arms of K at these joints. All results of the model simulations can be visualized in two figures. Figure A shows the position of the thumb chain and the direction of the external force K. The segments of the circle centered at the force application point visualize which muscles balance K. If the direction of K lies within the gray segment, K is balanced by FPL and EPL, which is counterintuitive. Within the yellow segment, K is balanced by EPL and EPB. Within the blue segment, K is balanced by FPL and EPB. Figure B shows a vector diagram that determines the forces in the muscles that balance force K. Without explaining the detail, the larger the striped line projections in this vector diagram, the larger the forces that balance K will be. Model simulations. The simulations A and B show large muscle forces in FPL and EPL, but the direction of K is in the gray segment. However, for K near or within the yellow segment, as in C and D, the muscle forces are small. The force directions in or near the yellow segment are balanced mainly by EPL in synergy with FPL or EPB. In conclusion, an optimal compensatory external force at the thumb tip is directed from distal to proximal at the thumb tip. With these force predictions, the video in the next slide can be reviewed. Observe the detail of the thumb index interactions. Observation of thumb support by index tip. The index persistently tended to flex its tip near the thumb tip. This deep flex position was in effect the index standby position between index string strokes. Occasionally, the thumb made forceful contact with the index tip. This contact sometimes extended to the index playing its string while maintaining thumb contact throughout the entire string strike motion. The thumb index contact was variable but seemed to have two main modes. First, contact at the apex of the thumbnail with the thumb IPG not hyperflexed. The contact force was then directed rather from distal to proximal as predicted by the model. Frequently, this contact involved the thumbnail pushing into the index skin, creating a skin indentation relief that allowed minimizing the transverse contact force component, thus bringing the contact force towards the distal proximal direction. Occasionally, the index pushed the thumb IP joint into its end position of flexion. This will be biomechanically analyzed in the next slide. Biomechanics of index pushing the thumb IP joint into its flexion end position. When the thumb IP joint is in its flexion end position, the thumb MCP joint is intrinsically fully controlled by the FPL and EPL-EPB. An external force is then redundant to achieve thumb control. Nevertheless, the video shows that occasionally the index pushed the thumb IP joint into its flexion end position. Theoretically, this might have some biomechanical benefit. Indeed, in the unloaded thumb, maintaining the IP joint in its flexion end position likely requires high FPL activity. When an external force pushes the IP joint into its end position, this FPL activity might be reduced while the thumb remains fully controlled. This would diminish the overall tension in the thumb. However, this benefit is theoretical, and the index-thumb interactions pushing the thumb IP joint into its end position seem to happen in transient dynamic rather than in static motions. Note that the functional direction of an index contact force pushing the thumb IP joint into the flexion end position becomes rather unspecific once the end position is reached. Indeed, any dorsal force on the thumbnail, however directed, that keeps the IPG into its end position can be balanced by the thumb muscles, because when the IP joint is in its end position, the thumb is intrinsically fully controlled. Some considerations on the variability and control compensations in thumb standby position. The controlling brain does not know mechanics. Therefore, the development of the compensations enhancing the controllability of the thumb would have been driven entirely by proprioceptic feedback. The video suggests that these control compensations converged towards the mechanical possibilities, but likely within a bandwidth of variability. In addition, there are two intrinsic mechanical compensation possibilities and even two different extrinsic compensation modes, notably index support with the thumb IP joint in or not in its flexion end position. Variability in motions will exist depending on which compensation modes will be active and by transitions between compensation modes during motions. A human observer, primed by the knowledge of the defect and the mechanical compensation possibilities, may recognize in the playing motions the different compensation modes and intermode transitions. However, in view of the multiple compensation modes and possible intermode transitions, it seems unlikely that from mere playing motion registrations, the mechanical compensation modes and the defect itself could be reverse engineered by system identification methods. Conclusion about the link between the flexor pollicis brevis dysfunction and the thumb dysfunction. Diagnostically, with respect to focal hand dystonia, the crucial question is, did the thumb have a motion control disorder? After all, the thumb did display playing motions that could be interpreted as dystonic cramping, namely severe FPL-EPL co-contractions and IP joint flexion into its end position. Biomechanical analysis. The apparent thumb dyscontrol was consistent with precise compensatory behavioral strategies to improve thumb control with a defective flexor pollicis brevis muscle. Intrinsically, mechanically, two compensation possibilities were effectively used: FPL-EPL co-contractions, which may generate an MCP joint flexion moment but requires large co-contractive forces, and IP joint flexion into its end position, which would result in a fully controlled thumb joint chain. Externally, the index tended to contact the thumb tip with specifically directed contact forces or by pushing the IP joint into its flexion end position. Conclusion. Mechanically speaking, the thumb did not seem dyscontrolled, but rather seemed highly precisely controlled in developing, by mere proprioceptive feedbacks, mechanically lawful compensations for the flexor pollicis brevis defect. Having clarified the biomechanics of the thumb dysfunction in slow playing, the next question can be addressed. What is the link between the thumb dysfunction and the index dysfunction in slow playing? In schematics, the thumb developed movement compensations for a defective FPB. These compensations fundamentally changed its control and playing motions. Part of these compensations was recruiting support from the index. The question here is, when the index is recruited to support the thumb, will the index playing motion still be effective? When recruited to support the thumb, the index gets two competing tasks. One is playing the strings. The other task is supporting the thumb. However, these tasks are in conflict. To pluck a string, the index must extend in preparation of the string stroke. To support the thumb, the index has to flex its tip deeply up to the thumb tip. General hypothesis. The fundamental hypothesis here proposed is that for the central nervous system, in locomotion, system controllability or operational safety has priority over task execution. An example of operational safety priority is limping. A joint in a leg can be kinematically intact but painful. This results in limping. The task is walking, but the central nervous system, triggered by feedback, has a second objective, in this case diminishing joint pain that results from loading the joint. Limping is an attempt by the central nervous system to modify the motion to minimize the load on the painful joint. This happens involuntarily. The limping changes task execution, likely making task execution less functional. For instance, a 100-meter track sprinter with a limp will likely fail in task objectives. The limping is a CNS-developed compensatory motor pattern superimposed on the normal task motor pattern. Limping also has priority over the task motor pattern. If not, with a kinematically intact joint, one could bite through the pain and walk or run normally. However, that would not be sustainable. Even with a kinematically intact but painful joint, a limping motor pattern would emerge. CNS control priority hypothesis applied to the case. Hypothesis: the index task of compensating for the thumb controllability defect gained priority over the index playing task. By this hypothesis, the index was permanently recruited to remain in flexed standby position near the thumb tip, ready to support the thumb. In the thumb support position, the index was much more flexed than in the normal standby position for string plucking, so that the index needed to extend excessively to strike a string. From the thumb support position, the index extended to pluck its string reluctantly and hastily, immediately returning after string stroke to the standby position for thumb support. Apparently, the task conflict in the index enhanced muscle tension and caused problems with properly extending the index in preparation for string plucking. It is in principle not excluded as an alternative hypothesis that the interaction of index and thumb resulted from a dystonic index seeking support from the thumb instead of the thumb recruiting support from the index. However, evidence that the thumb recruited support from the index and not inversely is provided by the differences in the playing behavior of index and thumb. The thumb readily abandoned index contact when plucking a string. In contrast, the index only hastily abandoned thumb contact or its flex position near the thumb tip to pluck a string, thereafter immediately returning to the flex position. The index, while flexed near the thumb tip, did not seek contact with the thumb. Contact was initiated or abandoned by the thumb. The index even played strings while the thumb maintained contact. The index remained in flex position even while having no contact with the thumb or when the thumb played strings. Biomechanically, the index had no defect and did not need support, testified by its normal functioning in fast playing. This video shows the phenomena discussed in the previous slide, including the index playing strings while the thumb keeps firm contact. Okay, continue. Presently, the question is addressed why, in fast playing, the thumb behaved almost normally. Why no FPL-EPL co-contractions in fast thumb playing? Static versus dynamic control of an unloaded joint chain. A first difference between fast playing and a static standby position is the following. By the multi-articular theorem, for static control, an unloaded massless joint chain needs one more muscle than a loaded chain. When in motion, the segmental masses create inertia forces in proportion to their accelerations. These inertia forces are equivalent to external forces, meaning that the joint chain is then in fact not unloaded. Therefore, it is possible that in the moving thumb, the muscles manage a dynamic equilibrium with the inertia forces that helps to suppress compensatory FPL-EPL co-contractions. However, this effect would be in conjunction with the compensatory control of the moving thumb described in the next slides. Control compensations in fast thumb playing. The video of fast playing, see next slide, showed that in fast playing the thumb motions were mainly realized at the CMC joint. This led to the following hypothesis of compensatory control of fast thumb playing. The muscles controlling the CMC joint position were intact, so the CMC joint itself was fully controllable, irrespective of the defective flexopolisis brevis. The intact CMC joint muscles were used to move the thumb in the unloaded phase of string strike as a stick, controlled at the CMC joint, while the MCP and IP joints remained in extension end positions. The biomechanics of this thumb control will be analyzed in the next slides. In this video, the three phases of fast thumb play can be observed. The MCP and IP joints remain extended as the thumb moves to strike the string. The loaded phase of the string stroke, when the thumb contacts the string, will be discussed in the next slides. Unloaded phase of string strike. CMC joint control in the O-plane. Controlling the thumb as a stick, moving at the CMC joint, requires simultaneous control of the CMC joint rotations in the P-plane and in the O-plane. In the O-plane, the CMC joint is controlled by mainly two muscles as antagonists, EPL and APB. The MCP and IP joints cannot move in the O-plane. This is prevented by their collateral ligaments, so their positions need not be controlled in the O-plane. This means that the control defect of the flexopolisis brevis exists only in thumb motions in the P-plane. Therefore, thumb motion control in the O-plane is fully independent of the flexopolisis brevis defect. Unloaded phase of string strike. CMC joint control in the P-plane. In the P-plane, CMC joint motions are controlled mainly by the APL, EPB, adductor pollicis and opponens pollicis. The stable control of the CMC joint in the P-plane by these muscles allows the extensor pollicis brevis and extensor pollicis longus to lock the MCP and IP joints in extension end positions, while the FPL can be inactive. When the FPL is inactive, FPL-EPL co-contractions are excluded. With inactive FPL, the volar plates will prevent MCP and IP joint hyperextension by the extensor pollicis brevis and extensor pollicis longus. With the MCP and IP joints locked in extension end positions, the extensor pollicis longus is decoupled from controlling the IPG position and becomes a dedicated CMC joint extensor in the O-plane. See previous slide. In conclusion, in the free phase of string strike, the thumb can be moved in the P and O planes as a stick controlled at the CMC joint with inactive FPL and the MCP and IPG in mobile in extension. Loaded phase in fast thumb motions. The loaded phase in thumb string strike is fundamentally different from the unloaded phase because the string contact introduces an external force. The video of fast playing, repeated in the next slide, showed that the musician used mainly two distinct methods to strike the string. A. String contact phase with the MCP and IP joints remaining extended. The CMC joint then flexed in the P plane and pushed the thumb tip through the string contact while the MCP and IP joints remained extended. B. A string contact phase with, after string contact, active flexion of the IP joint to plug the string. In that case, when becoming unloaded at string release, the thumb went through a transient, poorly controlled, jerky phase, with the IP joints continuing to flex, before resuming unloaded motion with the MCP and IP joints in extension end positions. Observe thumb behavior at and during string contact and at string release. Additional compensations. Increase of thumb tip motion perpendicular to the string plane. The videos also showed that in the thumb tip trajectory of string strike, the motion component OP perpendicular to the string plane SP was increased. A. Schematic of a normal thumb tip trajectory in string playing. The graph schematizes the thumb tip trajectory in the plane transverse and perpendicular to the string plane. The trajectory component OP perpendicular to the string plane is minimal. The realization of such a trajectory requires precise control of the thumb joints in the P plane. B. Thumb tip trajectory schematic in the musician in fast playing. The trajectory component OP perpendicular to the string plane was increased. Also increased was the amplitude in the O plane of the recoil of the thumb tip at string release. The increase of the OP component is mechanically consistent with the fact that in the O plane the thumb is only controlled by the CMC joint and that this control is unaffected by the flexopolysis brevis defect. Apparently, the increased OP component compensated for a deficit in thumb flexion control in the P plane. This video shows the increased OP component in the thumb tip trajectory. This OP component increase is variable and erratic between string strikes. Finally, it can also be observed in the videos that occasionally flexopolysis longus, extensopolysis longus co-contractions did occur in fast playing. However, this happened basically only when the thumb position became momentarily static, even at the briefest instance. Then FPL-EPL co-contractions, as in the standby thumb position, immediately appeared, including the tendency to hyperflex the IP joint. Moreover, when the thumb position became momentarily static, immediately the index tended to flex towards the thumb tip. In conclusion of why no FPL-EPL co-contractions occurred in fast thumb playing. Paradoxically, the most difficult control task with the defective flexopollicis brevis seemed to be doing nothing with the thumb, that is, merely keeping the thumb in the standby position of static, unloaded equilibrium. Theoretically, in this position, one muscle more is needed than in loaded static equilibrium. In fast playing, when the thumb was in motion, no compensatory FPL-EPL co-contractions occurred. By hypothesis, this happened for two reasons. First, the moving thumb is subject to inertia forces of the moving masses, which might increase the feeling of control. Second, thumb control of the unloaded phases was realized by the CMC joint, of which the muscles were intact. Thus the thumb was moved at the CMC joint while the MCP and IP joints remained extended. However, even at the briefest hesitation stagnation in thumb motion creating a momentarily static position, FPL-EPL co-contractions did appear, including the reflex of flexing the index tip towards the thumb tip. This brings us to the last of the biomechanical questions. Why was the index asymptomatic in fast playing? By hypothesis, index support was part of the compensations to improve control stability in the unloaded static thumb. Biomechanically, the benefit of index support at the thumb tip is that a functionally well-directed index contact force can equilibrate the thumb with normal forces despite the defective flexopollicis brevis. Such an external contact force might then suppress the FPL-EPL co-contractions on which the intrinsic thumb control compensations were based. However, in fast playing, while in motion, the thumb could be intrinsically sufficiently well controlled to suppress FPL-EPL co-contractions. Therefore, external support for the thumb was not needed and would also not be functional with the thumb in continuous motion. In consequence, in fast playing, the index was not recruited to support the thumb. For the index, then only the string playing task remained. Thus, uncoupled from thumb control, the index could freely use its original unaffected motor control patterns, displaying a superbly controlled playing technique. However, even the briefest stagnation of thumb motion into a momentarily static position instantly evoked FPL-EPL co-contractions, and with it the reflex of the index flexing for thumb support. The conclusions and diagnostic hypotheses are here schematically summarized. Both in slow and fast playing, compensations in thumb control were sufficient to allow the thumb to be functional in playing, to the extent that the musician did not perceive that the thumb had a control problem. In fast playing, the thumb control compensations did not involve the index. Therefore, the index playing motions remain fully functional and unaffected. However, the control compensations in the thumb in slow playing involved recruiting the index for thumb support. By hypothesis, in the index, the thumb support task dominated the task of playing strings, causing in the index a problem with the task of string plucking. End of part 2.